Good morning, everybody. Welcome to the lecture on lecture 5 on muscle force estimation using static optimization. Now, in this lecture, we will be discussing about mathematical modeling for muscle force estimation and will primarily focus on static optimization technique based on Lagrange multiplier method. The figure presented here is the overview of the muscle force estimation using inverse dynamics and static optimization. Experimental joint kinematics like joint angles, velocity and acceleration. The information on experimental joint kinematics is used to calculate joint moments and torques, joint moments or torques and joint forces using the inverse dynamics method. Now, joint moments or torques are the net combined effect of individual muscle forces spanning the joint. The contribution of each muscle can be calculated using a optimization scheme which we will be focusing on in this lecture. In some procedures, an initial guess of muscle forces is made on which the joint equilibrium is verified and changes in joint forces are made if necessary. The procedure is repeated until an optimal muscle force distribution is achieved. Now, let us consider indeterminacy in muscle force estimates. The figure presents the major muscle forces responsible for joint moments in the lower limb. As observed in the side view presented in the sagittal plane. So, these are the muscles. About 15 major muscles actually contribute towards the moments of forces at the ankle joint, the knee joint and the hip joint. So, that's about 15 major muscles that contribute in the joint moments across these three joints in the lower limb. At the knee, majorly there are about 9 muscles whose forces create the net moment. Now, important thing to note here is the line of action of each of these muscles is different and continuously changes with time. The other point to note is some muscles like bicep femoris, for example, may contribute towards moments around the hip joint as well as the knee joint. We continue with indeterminacy of the muscle force estimates, and we would like to say that to make a valid estimates of the individual muscle forces, it is necessary to consider a detailed anatomical or kinematic model with lines of action of each muscle relative to the joint center. Now, the extensor moment mj about any joint at any time instant t can be expressed as the net algebraic sum of the cross products of all the force vectors and the moment arm vectors. So, this is mathematically represented here in this equation. So, we can actually write down the extensor moment mj equal to the force vector cross product with the moment arm of the extensor muscles, and the other part is the same cross product of the flexure muscles with the moment arm of the flexure muscles. So, the sum of the cross products of all force vectors and the moment arm vectors, extensor in this case and flexures in this case, is represented together, and we calculate the net extensor moment mj. Now, in this equation, on the right hand side of the equation, we can see NE is the number of extensor muscles, whereas NF is the number of flexure muscles. Now, extension and flexions are just two opposite movements. The force of the ith extensor muscle at any time t is represented by Fei, and the corresponding moment arm of the extensor muscle is Dei, but always as a function of t, because we are taking into account the force at any instant time t. Similarly, the force in the ith muscle of the flexure. So, ith flexure muscle is represented by Fi, and the corresponding moment arm of the muscle at any time instant t is given by Dfi. So, the moment arm of the ith flexure muscle is given by Dfi. Now, let us discuss the first important topic on the mathematical modeling of muscle forces. Over the years, several mathematical modeling techniques in muscle force estimation or prediction have evolved. Before going into the details of the procedure, the need for such technique is discussed in this slide. The individual muscle forces are difficult to measure accurately, and there is no practical way to estimate muscular forces for a whole or even part of a system, musculoskeletal system, such as the upper or lower limb. Now, mathematical modeling can be used to predict these desired individual muscle forces. Even though the human body and its muscles are dynamic motors of the musculoskeletal system, static optimization is often relevant and gives satisfactory results depending on desired evaluation and purpose of the study. So, it may be noted herewith that the dynamic forces are then considered as static at every time instant. Let us now discuss about the mathematical modeling. When modeling the musculoskeletal human body, a set of force or moment equilibrium equations in the form of Ax equal to b can be formulated for the model structure where x represents the unknown muscular forces. Now, this set of equilibrium equations together with limiting values of muscle forces constrain the system. So, this is expressed here A, x and b. A is the coefficient matrix of the variable x and b is the constant. In mathematics, a set of linear equations or a system of polynomial equations is considered undetermined if there are fewer equations than the unknowns. An undetermined system can be solved with optimization theory. The optimal solution of a system is an admissible solution x of the minimum cost, where a suitable cost function Cx can be chosen rather freely. Since a muscle can only generate positive forces, constraints need to be prescribed on the system. So, this optimization problem is typically formulated as minimizing Cx subject to Hx equal to 0 and Gx less than equal to 0, where Cx is the cost function of the unknowns, Hx states a set of equality constraints and Gx is a set of inequality constraints. In the present context, equilibrium equations give the inequalities, whereas the range of possible muscular forces give the inequalities. Now, let us focus on the Lagrange multiplier method in the static optimization technique. The method of Lagrange multiplier is a strategy for finding the local maxima and minima of a function subject to equality constraints. This numerical method does not involve any initial guess. So, a system based on equilibrium equations as discussed earlier, Ax equal to b, together with the cost function Cx can be solved with the help of Lagrange multipliers. They convert the constrained minimization of Cx into unconstrained minimization. The Lagrangian function is expressed as presented in the slide, where Ax minus b represents the residual of the equilibrium equation. Mu is a set of Lagrange multipliers. Let us consider a sample problem to understand the optimization scheme. So, we consider a link segment of length twice L as indicated in the figure with 3 muscles F1, F2 and F3. We need to find out the expressions for the muscle forces in terms of known quantities with the help of Lagrange multiplier method. So, here in this problem, the known quantities are AI, DI, R1 and mg. AI is the area of cross section of a muscle, DI is the moment arm of a muscle, R1, R2 are the joint reaction forces as indicated in the figure. R1 is known in this problem and mg is the link segment weight. F1, F2, F3 are the muscle forces as indicated in the figure. The two endpoints of the links are A and B, and the angle Q is the angle between the axis of the link and the vertical direction. The length L is the distance of the center of gravity of the link from the end B. The forces F1, F2, F3 are the muscle forces as already indicated in the earlier slide. Only one equilibrium equation can be formulated for the unknowns considering the moment equilibrium. So, considering the moment equilibrium at B, the equation can be written as shown in this slide. Now, considering the equilibrium equation, the terms B and Ax can be separately written as shown in the slide. So, B is written here and Ax is containing the forces and the moment corresponding moment terms are written here in this slide. So, the B and Ax terms of the Lagrangian function is represented here in the slide, where B actually contains the moment of the segment weight mg and the reaction force R1. As you can see already in the slide, whereas Ax reflects unknown muscle forces and their respective moment arms. So, X is the set of unknown muscle forces F1, F2, F3, and D1, D2, D3 are the corresponding moment arms of the muscular forces F1, F2, F3 with relevant signs. Now, the cost function for the segment model can be written as a function of muscle stresses. It is actually written as 1/2 of the sum of the squares of the muscle stresses as presented in this slide. The Lagrangian function can then be formed and the minimum can be sought based on the Lagrangian function as presented in this slide. The Lagrangian function can be rewritten as follows. The Lagrangian function is indicated in the slide. The forces are replaced by the products of muscle stresses and the physiological cross-sectional area. The constrained minimal solution, please note here, very important statement, is then predicted by setting the differentials of the Lagrangian function to 0. Now, here as you can see, di is the moment arms of the muscles, R1, R2 are the joint reaction forces, mg is the segment weight, whereas F1, F2, F3 are the muscle forces, and A1, A2, A3 are the physiological cross-sectional area PCA of the muscle. Now, taking partial derivative of the Lagrangian function with respect to muscle stress, with respect to muscle stress and Lagrangian multiplier, we can write down the following equations. So, this is with respect to derivative, partial derivative with respect to muscle stresses, sigma 1, sigma 2 and sigma 3, whereas this equation is formed by taking partial derivative of the Lagrangian function with respect to Lagrange multiplier and setting it to 0. So, from the three partial derivatives as indicated here, equating to 0, we can express sigma 2 and sigma 3 in terms of sigma 1, and thereafter substituting sigma 2 and sigma 3 in the from this highlighted relations in the above equation as I have indicated, we can actually find out sigma 1. So, we have substituted the sigma 2 and sigma 3 in terms of sigma 1 in the equation as indicated in the earlier slide. So, we have only one unknown sigma 1 in the equation and we can solve out sigma 1. So, when we multiply sigma 1 with the corresponding physiological cross-sectional area of the muscle A1, we can easily find out the muscle force F1 as indicated in the slide. Eventually, the other forces F2 and F3 could be easily found out by multiplying the stresses with the respective physiological cross-sectional area. So, F2 and F3 has been found out as indicated in the slide. Now, in the example, if the muscle forces are not allowed to become negative, which is an important condition, the constraints Fi greater than equal to 0 has to be introduced by including the components Fi in terms of xi along with an extra set of Lagrange multipliers, which is indicated in the equation presented in the slide. This is an additional set of Lagrange multiplier introduced in the slide in order to include the constraint condition that forces in the muscle cannot be negative. Now, in this equation, G is a slack variable which is used to incorporate inequality in the Lagrangian function. Now, in a biomechanical context and with regard to an optimization scheme, the cost functions are sometimes called performance criteria to represent the performance which minimizes the activation of the muscular system. The assumption is that the body selects muscles for a given activity according to the performance criteria chosen. Now, various optimization approaches have been used over the years to solve the redundant muscle force or muscular force system. The main differences are how the cost function is set up and in the choice of the solution method. Typical performance criteria or function is the sum of muscular stresses, muscle stresses or forces raised to a power as indicated in the slide, where x is the muscle stress or force, n is an arbitrary integer greater than 1, and c can be used as a weighting factor. The table presented in the following slide will summarize different performance criteria used in different optimization studies carried out over the years. So, here we present a summary of the performance criteria and the solution methods used in the optimization. So, the system here lower limb, gait or upper limb, and we can see that there is a host of methods: simplex, Lagrange method, nonlinear programming, pseudo inverse algorithm. So, the reference of these performance criteria are indicated on the right hand side of the table. So, here you can see the criteria expressed in the second column. The x can be forces or stresses and n can vary from 1 to 3. M is the moment of all the joints included in the system, and V is the volume of each muscle. Fj are joint reaction forces or joint contact forces, and Fl are the ligament forces. Now, let us summarize the static optimization used in musculoskeletal modeling. A few important points. So, we would like to give you an overview of this technique used in musculoskeletal modeling. The musculoskeletal models along with static optimization method are used to study the muscle force distribution. The computational musculoskeletal models have increasingly been used for estimation of joint and muscle forces due to ethical problems associated with in vivo measurements of joint contact forces as well as muscle forces. Subject specific models have been used for more accurate estimation of joint loads for a variety of daily activities. A number of open source and commercial software are available for musculoskeletal modeling and simulation. Eminent open source software is OpenSim, and a commercial software is Anybody, for examples. In this slide, an overview of the joint force estimation has been presented. The schematic presents an overview of the joint force estimation using musculoskeletal model. First, a generic validated musculoskeletal model was scaled to the subject's dimensions and masses. Once the subject specific parameters are included in the model, as you can see here, inverse kinematics or inverse dynamics method can be utilized to obtain kinematic information of segments from marker data as explained to you earlier. Using ground reaction force data and kinematic information, joint forces and moments, as you can see here, can be calculated using the inverse dynamics approach. Thereafter, static optimization procedure can be employed to estimate the individual muscle forces considering the joint equilibrium. The joint reaction forces can be recalculated as indicated in this schematic overview. Now, this is a study by one of my PhD student, Basil Mathai, and the study has been published in Journal of Engineering in Medicine in the proceedings of IMECI Part H. Now, in this study, we actually evaluated the efficacy of few eminent musculoskeletal models regarding estimation of the hip joint reaction force. The results of one of the musculoskeletal models, the London lower limb model, is presented in this slide. In this slide, the joint forces were estimated for various activities like normal walking, stair up, stair down, standing up from a chair and sitting down during the stride cycle as indicated in the figures presented here. Now, the blue broken line represents the variation of the joint reaction force during different activities, and this result corresponds to the London lower limb model. Whereas, the pink line corresponds to the in vivo measured data of HIP 98 database. So, we are actually comparing the results of London lower limb model and the measured in vivo data. So, the figure actually presents a comparison of the hip joint forces estimated from the musculoskeletal model and the in vivo measured data of HIP 98. So, it is observed from the figures presented in the slide that the hip joint force estimated using the musculoskeletal model, London lower limb model, is very well comparable to the in vivo measured force at the hip joint of HIP 98 database. Please refer to the results presented in the paper as indicated in the slide for more details on joint reaction forces and muscle forces for different activities. Let us now state the limitations of this muscle force estimation method. So, muscle force estimation using musculoskeletal models and static optimization technique have the following limitations. The generic anatomy of the human body should be represented accurately as far possible. Objective function has no proven relationship between the actual distribution of muscle forces. The direct validation of individual muscle forces could not be achieved. EMG and in vivo joint reaction forces could be used for validation. However, generally the data availability is very limited. Inherent complexity associated with the mechanical properties of musculoskeletal systems is difficult to represent completely. Let us come to the conclusions of the study. When modeling the musculoskeletal human body, a set of force or moment equilibrium equations in the form Ax equal to b can be formulated for the model structure, with x representing the unknown muscular forces. In biomechanical context and with regard to optimization technique, the cost functions are sometimes called performance criteria to represent the performance which minimizes the activation of the muscular system. The references are listed here in 2 slides based on which the lecture was prepared. Thank you for listening.